In this video, we're going to talk about the idea of a linear transformation of a vector space. So again, this will probably be a review for a lot of you who have studied linear transformations in your linear algebra course, but we're going to put a little bit different spin on it here because of what we're using linear algebra for in this course. So here's a definition. Let's let V and W be vector spaces. A function T from V to W is said to be a linear transformation or linear map from V to W if it has the following properties. And those properties are, number one, for all V1 and V2 belonging to the vector space V, T of V1 plus V2 is equal to T of V1 plus T of V2. So in other words, the map T preserves addition. You might say that T is a homomorphism of additive abelian groups because every vector space is an abelian group under addition. And number two, for all V belonging to V and alpha belonging to F, the field of scalars, and I'm realizing now that I forgot to put that at the beginning of the definition. These are vector spaces over F, a field. And we're going to require that be the same field for V and W. All right, so anyway, for all V in the vector space V and all alpha scalars in F, we have T of alpha V equals alpha times T of V. And you'll notice here, there are two multiplications going on. This one is taking place within the vector space V, and this vector here is in W now, so this multiplication is happening in W. All right, so in other words, T preserves scalars, or scalar multiplication. And that's the definition. Now I'll just mention something here. Some people call this a linear transformation or a linear map, but some people call it a homomorphism of vector spaces. And when you look at the definition, you see that there are some properties here that are kind of reminiscent of homomorphisms. The one about scalar multiplication is a little bit different because you might expect to see maybe T of alpha times T of V, but you just have to remember that the transformation or map is mapping vectors, not scalars. So anyway, that's the definition. Now let's talk about one of the most important examples, or at least an important example for field theory. All right, so let's let H be an extension field of F. So H is a vector space over F. So it's a vector space with the scalars coming from the smaller field or the subfield F. All right, so here's my example. So first, let's fix an element A of H. All right, we're going to define a linear transformation, T sub A, from H to itself by T sub A of X, that says tax, equals A times X for all X in H. And you may wonder, okay, wait, why is that a linear transformation of H? In particular, why am I allowed to multiply by something that's not in the field of scalars? But, I mean, A times X is perfectly well defined. H is a field, so I can take any two elements of that field H and multiply them and get a result. And I'm going to claim that this is a linear transformation of F vector spaces. All right, or rather of the vector space H over F. So that's my claim. I'm going to claim that T sub A is a linear transformation. And the proof is actually delightfully straightforward. All right, so here's the proof. We need to verify it has the two properties. All right, first of all, the fact that T sub A maps from H to itself is not hard to see because we're just multiplying two elements of H. The result will always be an H. Okay, so let's check that T preserves addition and preserves scalar multiplication. All right, so first of all, if, what do we call them? Let's call them X and Y. If X and Y belong to H, then TA of X plus Y by definition is equal to A times the element X plus Y of the field. And because we're in a field and multiplication in that field is distributive, or I guess we say the field has the distributive property. We don't usually say the multiplication is distributive. But anyway, that's equal to AX plus AY. And that's equal to TA of X plus TA of Y. Awesome. Okay, so that means that we have the first property. And the second property is if X belongs to H and alpha belongs to F, that is the field of scalars, then TA of alpha X, well, what is that equal to? That's equal to A times alpha X. And then I can reassociate and commute so that I get alpha times AX, and that is equal to alpha times TA of X. So like I said, the proof is there's not that much to it. You have to convince yourself that everything you're doing is legal, and it is because all of these operations here, this one and this one, they're taking place within a field. Fields are pretty permissive, really. They're pretty reasonable. So this is a linear transformation. You may wonder why in the world we would care that this is a linear transformation. It seems like it was so easy to prove that you wouldn't think there would be a huge payoff in knowing it. But in the next video, we'll see what's actually kind of cool about this example.